So hi everyone, I'm Nathan. I'm going to be talking about an improved approximation algorithm for the traveling salesperson problem in the half integral case. And this is joint work with Anna Carlin and Cheyenne Oveskaran. So I'll quickly remind everyone the definition of TSP. They're given as input a list of cities and their pairwise symmetric distances, which form a metric. And the goal is to find the minimum cost tour which visits every city at least once. TSP is NP hard, so often we must resort to approximation algorithms to find solutions. The best known approximation algorithm is from Christofides in 1976, and there's a 123 over 122 hardness result. There's been a lot of exciting work on approximating metric TSP and related problems since Christofides. However, there's been no improvement to this 3/2 ratio in the general case. So a major open question remains, can we beat 3/2 for general metric TSP? One of the key tools in approximating TSP is this linear programming relaxation. It essentially asks for a fractional Hamiltonian cycle. So every vertex should have fractional degree 2, and every cut should have fraction at least 2. And this is known as the subtour elimination LP or the Held-Karp relaxation. Given this LP, we can define our special case of interest called half-integral TSP. And it simply means that when you solve the LP relaxation, every edge is 0, 1/2, or 1. So this graph on the right is half-integral. This sounds a bit artificial maybe, but there are some good reasons for studying this case. First, the best known integrality gap is a half-integral graph. And second, there's a conjecture that half-integral instances actually obtain the integrality gap from Schallekamp-Williamson and Van Zuylen. But maybe most importantly, it's sort of a good testing ground to sharpen our methods. Half-integral TSP offers a pretty simple structure, but has up until now resisted attempts to improve upon Christofides' 3/2 approximation. Okay. You can think of our problem input as a 4 regular, 4 edge connected weighted multigraph. This is an equivalent input, and you can see this by just beginning with the support graph and substituting all edges with x equals 1 with 2 edges of x equals 1/2. So the resulting graph is 4 regular and 4 edge connected. And for the rest of the talk, I'll be referring to this input format. So every edge I talk about will have x equals 1/2. As our main result, we show that we can beat 3/2 for half-integral instances of metric TSP. And this shows that if the conjecture I mentioned is true, then the integrality gap of the subtour polytope is bounded away from 3/2. And I think this should give researchers some hope for beating 3/2 in the general case. Okay, so to give a brief outline of the rest of the talk, first I'll go through the algorithm and a key ingredient for understanding its approximation factor called the matching LP. Then I'll go over the main ideas of the analysis before completing it with some simplifying assumptions by applying properties of the spanning tree distribution we use in our algorithm. So here we'll study an algorithm which is based on work by my co-author Cheyenne, as well as Sabarian Singh. And it's identical to Christofides' algorithm, except in the choice of the tree. So first we'll carefully choose a spanning tree based on a linear programming solution. So this step is different from Christofides' algorithm. We carefully choose a tree instead of just choosing a minimum spanning tree. But even though the graph is connected, this is not a valid tour yet because some vertices have odd degree. So now we add the minimum cost matching on the odd degree vertices of the tree. And our goal is now to use properties of the tree to show that the expected cost of this matching is less than half of the LP in expectation. And since the tree costs the most of the LP, and if we can show this, then we would have a better than 3/2 approximation. So this is going to be our goal. So to bound the cost of the minimum cost matching, we're going to use this matching linear program. And what's nice about this is it has an integrality gap of 1. And we use this because it's much easier to get a handle on the cost of a fractional matching than it is to understand the cost of an integral matching. And due to the lack of integrality gap, we sort of lose nothing in this step. So we might as well think about fractional matchings. This second constraint may look a bit unintuitive, but you can derive this from the fact that if this is a tree, the tree we want to add a matching to, and in red are the odd vertices, if you select a set whose cut has an odd intersection with the tree, then there must be an odd number of odd vertices inside this set. So at least one of them must be matched to a vertex outside the set, letting us add this constraint. And our goal for the rest of the talk will be to show that there's some procedure which for every tree that could be sampled by our algorithm builds a fractional matching. And we'll show that the expected cost of this fractional matching is less than half the cost of the LP. And using this integrality gap fact would give us the result. And the expectation here, just to be clear, is over the randomness of the trees. So it's interestingly actually very easy to get a matching of cost at most half of the LP. If we set y equals 1/4 everywhere, where here we think about this 4-regular graph where every edge is 1/2, this is already feasible since every cut contains at least 4 edges. So we simply satisfy this second constraint for every cut, not just the odd ones. This costs half of the LP as we've just divided every edge in 2. And so we immediately recover the 3/2 approximation of Christofides. However, as I said, this assignment satisfies every cut, not just odd ones. So here's the hope. Maybe if many cuts actually have an even intersection with the tree, we can gain. We can reduce this 1/4 to maybe something less on average. And that's going to be sort of exactly our goal. So we're going to try to show that for some randomized fractional matching procedure, its expected cost is strictly less than 1/4 for every edge. And just one bit of notation, I'm going to say a cut is even if the number of edges in the tree intersected with the cut is even, and odd otherwise. So this green cut is even, this red cut is odd. Okay, so our approach is going to be to start from this feasible solution, this 1/4 everywhere vector, and then sort of make a step in a direction that makes the cost cheaper. And we'll guarantee that when we make this step, no YE value will ever be reduced below 1/6. And it turns out that this guarantee implies that the only constraints we have to worry about are the minimum cuts in the support graph, in this 4-regular graph. So why is this? Since 4-regular graphs are Eulerian, every cut either has 4 edges or it has at least 6 edges. So by ensuring YE is always at least 1/6, we can just focus on the minimum cuts of the support graph. Even if I reduce every edge in this green cut, this constraint is still satisfied, even if the cut is odd. So in other words, using this strategy, we only need to worry about the structure and the parity of the minimum cuts, and nothing else. And it turns out this approach is sort of doomed if minimum cuts are always odd in the trees we sample. So it'll be important to sample a tree that makes sure minimum cuts are even with some probability. Okay, so how will we sample our tree? Here's the Held-Karp linear program again. And notice that if you set ZE to 1 - 1/n times XE, then Z is in the spanning tree polytope. And feel free to just believe this. And now we can sample a tree from Z by writing Z as a convex combination of trees and sampling one. So this is good. Now the tree we sample respects the marginals of the LP, up to some 1 - 1/n factor. And every minimum cut has expectation 2. So maybe we can hope that every minimum cut will actually be 2 and hence even some of the time. However, this is not every convex combination we can write will work. So for example, the complete graph on n vertices can be written as a convex combination of stars. And here the minimum cuts are just the degree cuts, the vertices. But in every star, every vertex is odd. So some convex combinations do not work. And to be clear, the issue here is that even though the expectation of every minimum cut is 2, our distribution doesn't concentrate at all. So the degree of every vertex is either 1 or n minus 1. So how should we sample a tree? What's the right convex combination? You might notice that if you go out into nature, most trees actually are pretty good. This tree on the left has a lot of, say, even vertices. The tree on the right is not so good. It looks like a star, but I'm not so sure the thing on the right is even a tree. So this suggests the question, what about random trees for some definition of random? It's well known that uniformly random spanning trees are negatively correlated, and so obey these concentration properties. And we know similar things for so-called lambda uniform spanning trees, where every edge has weight lambda e, and the probability of a tree is proportional to the product of the lambda e's in its edge set. So for example, this graph on the left with lambdas 1, 2, and 4 would yield the following convex combination of trees. This sounds great. We would get some concentration, but it's not clear how to find a lambda uniform distribution that respects the marginals of our LP. Thankfully, in 2010, for an application in asymmetric TSP, Asadpour, Gomans, and their co-authors showed that this can actually be done. We can find lambda e's in polynomial time such that the marginals of the edges and the resulting lambda uniform distribution are preserved. This can be done by finding the maximum entropy distribution, which respects the marginals via a convex program. And the lambda e's will be encoded in the dual of this program. And now we have the properties we want. We preserve marginals, and we have negative correlation, concentration. And now minimum cuts should have a good chance to meet their expectation and actually have even intersection with the tree. And this is the set of properties that Ovescaran, Saberi, and Singh used in 2010 to show a better than 1.5 approximation for graphic TSP. Max entropy trees have a lot of nice properties. However, for now, we'll just use one, which is unfortunately not strictly true, but we'll assume it for the talk. So we'll assume that any two minimum cuts are even simultaneously with some constant probability p. Okay. So given this, how might we gain? Remember, we want to start at this feasible vector 1/4 everywhere and then perturb it to yield a cheaper point. And we also guarantee that we never reduce an edge below 1/6. So first, let's try the obvious thing. We'll just set an edge to 1/6 if it's in no odd minimum cuts and 1/4 otherwise. If every edge had some probability p of being in no odd minimum cuts, this would work. However, this fails because some edges may be in many, many minimum cuts. And sort of these edges in many minimum cuts may be the expensive ones. Remember I said we have to sort of gain on every edge in the support graph. And the solution to this, which I'll explain in a lot more detail, is to use an inductive approach by building a hierarchy of minimum cuts. Okay. So let's get a feel for why this might work. Let's consider sort of the base case, where the only minimum cuts of the graph are the degree cuts, the vertices. And I claim, given our assumption, we're already done. So pick any edge E, its two minimum cuts are its two vertices. And with probability p, as I said, the tree we sample has even intersection with both endpoints, with both of its minimum cuts. So in this regime, the strategy I mentioned works. With some probability p, every edge is in no odd minimum cuts. And in this event, we can reduce it to 1/6. So now every edge has expectations strictly less than 1/4, beating 3/2. So the base case works. Okay. So now I'll move on to the algorithm from our paper. It turns out that our algorithm only has a minor difference from the one from Ovescaran, Saberi, and Singh, which was to sample the tree from this scaled down version of the LP. Basically, our algorithm is equivalent to sampling a maximum entropy 1 tree, or a tree plus an edge, i.e. not scaling down the LP first. However, our algorithm is best described in a different, more combinatorial fashion. And actually, this combinatorial algorithm was how we first approached the problem, and we found the equivalence a bit later. So first notice that if we choose any minimum cut S and zoom in on the vertices inside of it, the point z equals x is in the spanning tree polytope for the vertices inside of S. So we can compute the maximum entropy distribution of the set S and sample a tree. So our algorithm will continuously choose a minimal minimum cut with at least 2 vertices, choose a spanning tree inside of it from the maximum entropy distribution on that set, and then contract that set. So continuing a run of the algorithm, here we pick another min cut, pick a tree, and contract it. And again. Here I'll do 2 at once. And it turns out that at the end, we always get a cycle. And we'll just choose a cycle at random. So this algorithm immediately gives us a very useful independence property. It says that any edge inside a minimum cut is independent of the edges outside of it. They're chosen just from different distributions. I'll demonstrate this visually in a second, but just to summarize the algorithm, while there exists a minimum cut of size at least 2, we pick a minimal such cut S. Then we compute the maximum entropy distribution inside of S and sample a tree from that. Then we contract S. And at the end, we choose an arbitrary cycle, and we return the union of all the edges we've chosen. And as I said, we ultimately sample a tree plus an edge, a 1 tree. So this gives rise to a hierarchy of minimum cuts based on the order in which they were contracted. So in other words, a hierarchy based on containment. And this is the tree we just constructed. And adding back the edges, here the edge E is in 4 minimum cuts, 2 containing its left endpoint and 2 containing its right endpoint. And here we say that L2 is higher than L1 and R2 is higher than R1 in this hierarchy. So here F would only be in 2 minimum cuts. So as I mentioned, this gives rise to a nice independent structure. So here any event in one edge color is independent of any event in any other edge color. And this is just by virtue of the algorithm. And here it is without the overlaid cuts. And this is quite useful. It means that in our inductive argument, we can sort of cleanly separate events that occur at different levels. So now I'll discuss the general approach to analyzing the cost of the matching. So one thing I've swept under the rug with this algorithm is that minimum cuts may actually cross. And this makes the hierarchy just a little more complicated. So to avoid this, I'm going to make an even stronger assumption, which is that no 2 minimum cuts share more than 1 edge. And it turns out this implies that no 2 minimum cuts cross, which essentially follows by the submodularity of the cut function. And it turns out that 2 crossing minimum cuts in a 4-edge connected graph have exactly this structure. And I won't go into it, but this rigid structure actually makes it fairly easy to deal with cuts that are crossed. So the hierarchy does not get much worse. But either way, throwing out the notion of crossing cuts for now, we really do have an unambiguous hierarchy, a laminar family ordered by containment. So now that we've described the algorithm to construct the tree, I'll go back to talking about constructing the fractional matching. We'll decrease edges in exactly the same way as in the base case if its top 2 cuts in the hierarchy are even. So for example, look at this edge E. L2 and R2 are its top 2 cuts in the hierarchy. And suppose we sample this tree, black edges represent the tree. Here we would not reduce E because both L2 and R2 are odd. If we sample this tree instead though, here both L2 and R2 are even, and we're going to reduce YE from 1/4 to 1/6. However, we only condition on L2 and R2 being even. We don't know whether L1 and R1 are even or not. And if they're odd, we've actually violated the constraint in the matching LP. So we'll actually increase other edges to make up for this decrease. So in this case, R1 is odd. So we must increase F1, F2, and F3 to make up for the reduction in E, to sort of fix this constraint that we violated. And the rule will be to split the necessary increase between all edges which end at the level of the violated constraint. So in this case, F1, F2, and F3 are inside the level of R1. So they each increase by 1/36. Something important to keep in mind is that if an edge is reduced, it definitely does not have to increase for any edge going higher. This is because it is only decreased if both cuts that it would have to increase for, its top cuts, are even. So the increase and the decrease events are disjoint, and it only remains to show that the expected decrease is greater than the expected increase. So just to summarize where we are, we start with the all 1/4 vector. We decrease ye by 1/12 if its top two cuts are even. This process might violate some constraints. And so sort of for cuts that are lower in the hierarchy, and for these, we increase the ye value of edges which are at that level in the hierarchy. So let's think about how to analyze the expected value of an edge in the O-join. A simple but important idea we use is we reduce every edge with the same probability. For every edge, we'll choose a random subspace of the event in which the edge is even in its top two cuts of measure P. This sort of equalizes the edges and ensures that no edge has to increase more than it decreases in expectation. So let's compute the expected ye. For an edge E, by our assumption, at most one edge on each of its top two cuts goes higher. So here, F and G go higher. E is reduced by 1/12 with probability P. And now let's look at the expected increase for F. For G, it's similar. So this is the probability that F is reduced, which is P, times the amount of reduction, 1/12, divided by 3, since we split the reduction with E1 and E2. And finally, we only need to perform this increase if U is odd and F is reduced. So hence this conditional probability. And some of you might see that even if these probabilities are 1, we're done. But once we relax some of the assumptions I've made, we'll need this to actually be a somewhat good constant. So to get this, we need to look at some properties of our tree, properties of our distribution. So I talked about lambda uniform distributions earlier in the talk. And it turns out these distributions are what's called strongly Rayleigh. So let me define this quickly. Consider a distribution mu over subsets S of a set M. Let mu of S be the probability that S is selected. Then we say the distribution is strongly Rayleigh if its generating polynomial is real stable. And we call a polynomial real stable if it has no zeros in the upper half of the complex point. So if I set all of the zi's, where zi's represent edges here, to have positive imaginary value, then the polynomial is real stable if it cannot be 0 when these values are, imaginary values are positive. Okay. So SR distributions have many desirable properties, but one of my favorite is this, and I'll put it in terms of our spanning tree distribution for clarity, but it holds in general. This property is that for any cut S, there exists some number of Bernoullis such that the law of the size of the intersection of this cut with the tree is equal or the same as the law of the sum of these Bernoullis. So in other words, for any k, the probability the size of the intersection with the tree is k is exactly given by the probability these Bernoullis are k. And this gives us a good constant. It says that for any minimum cut in a half integral graph, it's even in the tree with probability at least 13/27, so very close to 1/2. And now we can bound the probability that U is odd given that F is reduced. And I won't go through this due to time, but feel free to pause the slide and work through it. It follows from independence of F from E and any event inside of this blue cut and this Bernoulli fact that I just said. So to summarize, we use the structure of minimum cuts, the independence properties of our algorithm, and the properties of strongly Rayleigh distributions to bound the expected cost of each edge in the matching LP below 1/4, yielding a better than 3/2 approximation for half integral instances. So next steps, the first obvious question is whether there is a reductions to half integral case, whether this conjecture is true, or whether there's an improved analysis here. I think it would be very nice to get 4/3, but maybe even 1.48. I think 1.48 is maybe doable with our methods, but 4/3 would need a big innovation. Maybe more importantly, can we extend this analysis to the general case? And my co-authors and I are optimistic about this, but we ask whether there are totally new approaches to analyzing this algorithm. Max entropy trees offer quite a lot of structure and independence. So with that, thanks for listening. If you're interested in hearing more details, there's a link to an hour-long version of this talk in the comments. Looking forward to hearing any questions and comments in the session. Thanks.